In this next part of our series on the chemistry of life, we talk about water. Now, in the previous review, we talked about what made water a polar molecule in the first place. You've got different electronegativities between oxygen and hydrogen, so that makes water a polar molecule, with this end being partially negative, this end being partially positive. And of course, a hydrogen bond is what forms between the positive and partial negative ends of the water molecule. Now, notice I only drew one hydrogen bond. A water molecule can form up to 4 at a time, but they don't always do that. But this will pull the molecules toward each other, and this affects all of the properties of water, which I have listed here. So of course, water can exist as all states of matter, liquid, solid, and gas. And of course, with liquids, the molecules are fairly close together, rolling around. With a solid, they're vibrating but more or less staying put, but in a gas they're moving randomly. Now, if it wasn't for hydrogen bonding, water would not exist on this planet as a liquid. It would all be a gas, because if we compared this to a nonpolar substance such as methane, there's no attraction, and methane is a gas. Now, you also have surface tension, which means at the very top of the water you have sort of a more stable field of molecules where they're forming more hydrogen bonds at the same time. But this also allows for other things, such as capillary action, where water can climb up tiny tubes and things like that. Now, moderation of temperature. When it comes to heat and temperature, heat is molecular motion. So more molecular motion means more heat. Now, when we're getting this to heat up, we're overcoming the forces that would prevent their movement. So in other words, it takes a lot of heat to raise the temperature of water. We call this high specific heat. Specifically, it takes 1 calorie of heat to raise 1 gram of water by 1 degree Celsius. That's a lot higher than most other substances. And for that reason, it takes a lot of heat to raise the temperature of water. And it also takes a while for the water to cool off. Thereby, water moderates temperature. Water also has a high heat of vaporization. Now, of course, the boiling point of water is at 100 degrees Celsius under standard conditions. So it's going to take 1 calorie to raise 1 gram of water from 99 to 100, and it's going to take an additional 540 calories to vaporize that gram. That's a lot of heat. But water evaporates anyway, and thereby it removes heat. We call this evaporative cooling. That's what happens when we perspire or sweat. Another property of water is that ice floats. Well, you might be thinking, so what? Well, it kind of is a very big deal. It's very unusual for a solid to float in its own liquid, because solids are usually denser than their liquids and would sink. Contrast that with ice, which is less dense than liquid water. Now, the reason why, again, has to do with hydrogen bonding. Water gets colder. When you cool off water, it does become more dense. To a point, it reaches its maximum density at about 4 degrees Celsius. And then, because the molecules are going so slow, they're starting to form more hydrogen bonds simultaneously. And with each water molecule is forming all 4 with every other one, the geometry of the bond angles, they can only be so close together and do that, and it forces them to spread out. This is why ice expands when it freezes. That's why ice floats on water. Water is also a versatile solvent. A lot of things can dissolve in water. And things that dissolve in water are called hydrophilic, water-loving. Well, other polar substances such as sugars and salts, which are electrolytes, they mix well with water. Now, things that don't mix well with water are known as hydrophobic. These are the non-polar molecules, such as oils and so forth. Now, the fact that some substances are hydrophilic and some substances are hydrophobic, this property allows for cell membranes to exist. That will be explained later when we talk about phospholipids. Now, another part of the discussion of water is pH, acids, and bases. Now, to understand pH, we have to again talk about what's happening with pure water. Well, in small amounts, a water molecule will dissociate into its ions, the hydrogen ion and the hydroxide ion. In reality, this joins another water molecule to form hydronium, but we're leaving that part out. But what this means is that in pure water, for every one of these that breaks, you've got one of these and one of these. So therefore, the concentration of the hydrogen ion, written like this, is equal to the concentration of the hydroxide ion. And the actual hydrogen ion concentration is 10 to the minus 7 molar. That's where the 7 comes from in the pH scale. pH is the negative logarithm of the hydrogen ion concentration. In other words, that exponent dropping the minus sign. So here we have the pH scale ranging from 1 to 14. 7 is neutral. Numbers below 7 are acidic. Numbers above 7 are basic. An acid is any substance that raises hydrogen ion concentration, such as hydrochloric acid, in which case these outnumber these. A base is the opposite. It lowers hydrogen ion concentration. In other words, there's less of these than there are of these. So sodium hydroxide. Now, hydrochloric acid mixed with sodium hydroxide in equal amounts neutralizes the other, and you end up with sodium chloride and water, salt and water. So acids and bases have the ability to neutralize each other. And of course, we have to have pH balanced in our body fluids. Thereby, we have buffers. Buffers are combinations of weak acids and weak bases that counteract other acids and bases to balance pH by opposing change. And that ends this review.